All right, today we are diving into a concept that's pretty much everywhere, powering everything from your Netflix queue to medical breakthroughs. We're talking about conditional probability. So, ever wonder how Netflix just knows? I mean, it's not psychic. It's actually calculating the probability you'll love one movie given that you've already watched and liked another. And that little word, given, that's the whole secret sauce. That's our entry point into conditional probability. Okay, the best way to really get a grip on this is to picture it. Don't think about formulas, not yet. I want you to imagine probability as this giant universe of possibilities. And with every new piece of information we get, that universe, it shrinks. So here's our starting point. This whole grid of hexagons, that's everything that could possibly happen. It's our entire sample space. You've got the red area, event E, and the green area, event F. Right now, in this moment, anything's on the table. But then, something changes. We get a new piece of evidence, a fact. Someone tells us with absolute certainty that event F has happened. Suddenly, our entire universe of what's possible is about to get a whole lot smaller. And just like that, our world changes. See? All of those hexagons outside the green F area, they're gone. They're impossible now. Our new reality, our new sample space is just those outcomes inside of F. We've conditioned on F, and our universe has literally shrunk. So if we ask, okay, in this new reality, what's the chance of E happening? Well, we can't look at the whole red area anymore. In our new, shrunken world, the only part of E that's even possible is the bit that overlaps with F, the intersection. Those three hexagons are all that's left for E. So our intuition is screaming at us, right? The new probability has to be that overlapping part divided by the size of our new, smaller world. Now let's just translate that gut feeling into the language of math. And here it is. This is the formal rule, and it's exactly what we just visualized. The probability of E, given F, and that vertical bar just means given, is the probability of them happening together, the intersection, divided by the probability of our new universe, F. It's the piece of E that's still in the game, scaled to the size of our new reality. Now, what's really cool is if you just do a little algebra on that same exact formula, you get another super powerful tool, the multiplication law. This lets us find the probability of two things both happening. It's the chance of the first thing times the chance of the second thing, given that the first thing already happened. So, we've seen how knowing about one event can totally change the odds of another. But what if it doesn't? What if finding out about one event tells us absolutely nothing new? I mean, that's a fascinating question, right? What happens if learning that F occurred doesn't change the odds of E one bit? It's like the new information was completely useless. Well, this special case has a very important name, independence. And here's the official definition. Two events are independent if the conditional probability, P of B given A, is exactly the same as the original probability of B. It means knowing A happened gave us zero new info about B. The odds were, and still are, just P of B. And this simple idea gives us a really practical, really powerful way to check if two events are truly independent of each other. And this is the big one. This is the test you'll use all the time. Two events are independent if and only if you can just multiply their individual probabilities together to get the probability of them both happening. It makes perfect sense if you think back to the multiplication law. If P of B given A just equals P of B, the formula simplifies to exactly this. Okay, now we have to talk about this because it's a super common point of confusion. People often mix up the idea of independent events with mutually exclusive events. And they sound kind of similar, but in probability, they are almost polar opposites. So let's put them head to head. Independent means they don't affect each other at all. Think about slipping a coin twice. The first toss has no say in what the second one does. Mutually exclusive, on the other hand, means they can't possibly happen at the same time. Think flipping one coin once. It's either heads or tails. It can't be both. This table is where it all clicks. For independent events, sure, they can happen together. But for mutually exclusive events, the probability of them happening together is zero. And look at that second row. If two events are mutually exclusive, they are actually extremely dependent on each other. If you know A happened, you know absolutely everything about B. Its probability just crashed down to zero. So here's the big takeaway. If you have two events that can actually happen, they can never, ever be both mutually exclusive and independent. One means no influence, the other means total influence. They just can't be the same thing. And that really brings us back to the heart of it all. This isn't just a bunch of abstract math. It's a system for learning. It's how we formally quantify the process of changing our minds, of updating our beliefs when we get new evidence, shrinking the universe of possibilities to make smarter bets about the future. So we figured out how to calculate the chance of a symptom given a disease. But what a doctor really wants to know is the other way around, right? What's the chance the patient has the disease given that they're showing the symptom? Can we flip this thing around? The answer is a resounding yes. And it leads us to one of the most powerful theorems in all of science. But that is a story for another time.